Hello everyone, I'm Anil Chowdhury. I'm a principal scientist at Applied Optimization, and today I would like to speak to you about our SBIR Phase 2 project N181-085. It's about feed-forward controls for laser powder bed fusion. Specifically for feed-forward controls, we respond to a sensor signal that is collected on a layer-by-layer basis, and we respond in a predefined manner based on a mathematical model that we have developed for process simulation. And our goal is to produce high-quality as-built parts, ideally with no at-surface or near-surface defects, since those defects cannot be healed by HIP.
At Applied Optimization, our focus is to attain high quality in metallic additive manufacturing, particularly by eliminating or mitigating at-surface and near-surface defects and minimize interior defects. The focus on at-surface and near-surface defects is because these defects cannot be healed by HIP. We also want to be able to compensate for AM process variability using real-time process control, particularly using science-based, physics-based mathematical modeling, predict location-specific build quality using non-C2 non-destructive testing. Our technical history is that we have received 4 awards in the last few years. One was a $40,000 DARPA award for part scale modeling. Second was a NIST AM benchmark model for solidification, grain structure, and orientation modeling. The third was an award in Air Force Challenge for modeling of melt pool evolution as a function of scan path. And the fourth was the America Makes Award for developing innovative algorithms for scan path modeling. Our key resources which have made these things possible is our ICME software for additive manufacturing parameter prediction, which is used to specifically define location-specific or feature-specific parameters which are designed to mitigate defects. Anomaly flagging and anomaly correction, which is for correcting and process control. We also have expertise in sensor characterization, fabrication of optical components, and special sensing devices. The Navy challenge is to use process control and AM process modeling to improve quality of as-built AM powder bed parts. So we have here, as an example, a link, which is a titanium 6-4 part. And on the right side, you see the part that was produced. And you will notice that there are no defects at surface and near surface. So when this part is subjected to HIP, the defects will heal in the interior, and there is a solid shell on the outside which can give you a good quality part. The methods that we are developing are generic in the sense that although we are using link as a sample example for demonstrating, the method is generic because it is based on physics-based models and mathematical algorithms for adjustments of the process. So we have developed process control hardware, software, and models to compensate for inconsistent temperature distribution, residual heat buildup, and melt pool formation. Our transition target are really for different systems where the need is to produce structural parts and make use of digital thread for making the process compensation in real time as the part is being built. The operational need and improvement is to really take care of the technology gap, which is to account for a system physical property variability in the powder bed AM. And specifically, we would like to be able to compensate the AM processing parameters and scan path track vectors during the AM powder bed process and improve build quality. So there are two things that we do. On the top left, you see there is an anomalous region that is detected through in situ sensing. When such a region is detected, we adaptively change the scan path. All parameters, power, velocity, line spacing, core offset, contour offset, rotating scan path direction, and so on, and apply corrective action, including powder recoat, only in the anomalous regions to correct the anomaly. The second thing that we do is an off-axis sensing device, which allows us to collect high-resolution data anywhere in the build plane in visible and mid-wave infrared wavebands. And this data then is processed on a layer-by-layer basis to identify and correct anomalies. The technology developed is laser powder bed process control with layer by layer and track by track update for full set of scan path and location specific AM processing parameters. Our salient development is to use in situ process monitoring data to flag build anomalies, update scan path, and feature specific process parameters on a layer by layer and track by track basis to improve build quality. We also collect high resolution, simultaneous visible and infrared in situ sensing data anywhere on the build plane using a hardware that we have developed called as the open sensor interface, whereby one can plug in third-party sensors of different kind in order to adapt your sensing to the type of build that we are trying to make. Our key points in the R&D is to be able to compensate for physical property variability on the basis of mathematical models so that the method developed is applicable in general to a wide variety of complex parts. The specs Ritchie acquired is that we have been able to demonstrate reduction in build defects and surface roughness. And the key innovation is to account for the interaction between the scan path and the complex part geometry to adaptively control the scan path and powder bed processing parameters. The current status of our program is that we have demonstrated a true laser powder bed process parameter control. Our focus has been on feed-forward process control, although we have also implemented feedback process control. The feed-forward process control can be implemented on commercial laser powder bed systems. The feedback requires a research type of system. We've demonstrated laser powder bed layer-wise scan path track vector update. We developed our first prototype in December. Our final prototype is now in March. And we are demonstrating the ability to improve quality for a complex part. And we are going to repeat that for a build or two more between now and the end of our program. The key features, advantages, and benefits of our work is that the anomaly flagging, control, and process modeling are commercial products that we have developed. One is AFS, second ACS, and third AMP2. So these products provide unique developments as compared to the current process, which is where we select AM process parameters based on prior experience and AM process modeling. The improved process is to detect and correct build anomalies on a layer by layer, track by track, and point by point basis to improve the laser powder bed AM quality. So essentially, the way this can work is where you assign default parameters that are used for producing a part, and the process control is then used to adjust the process as the part is being built in order to improve its quality. It also has a second benefit, that the output of the process control is to really demonstrate or to convey what are the types of adjustments that had to be done in order to improve the part quality. The knowledge gained from the process control can be used for subsequent builds in order to build better processes. For transition to fleet, the need for technology transition for us beyond phase two is an opportunity to produce a full-size complex structural part and demonstrate improvement in AM build quality. This is because the work that we have done is based on physics-based models and mathematical theory for process control, and therefore it is applicable to a wide variety of parts, complex geometries, part families, etc. We currently have support for transition from an aerospace OEM. We would like to also develop transition support within the DoD. We are trying to develop for additional in the commercial arena. Specifically, what we are looking to do is to demonstrate AM process control for a specific platform and opportunity to develop improved as-built parts, high quality, which is a critical step towards AM process qualification and wider application of AM process technology. Our market analysis for process control is there are widespread applications across commercial DoD Navy arising from the increasing need to produce as-built high-quality AM material for complex parts, particularly for industrial machinery, oil and gas drilling, medical applications, data centers, etc. And particularly also for structural parts with complex dynamic loading during its operational environment. Indeed, there are so many applications, it's not really possible to cover them in this quick presentation. And I would like to request you to please reach out if you have a specific application or a part in your mind for which you would like to see how process control can benefit in developing the AM process and save significant amount of money and time. I would like to urge you to reach out to me, and I believe we can adapt our or apply directly as is the methods that we have developed to your application. And that's simply because everything that we have done is based on hard physics-based concepts and mathematical modeling. Our transition/partnership pitch to you is that we would like to demonstrate how you can save time and money by using process control to produce structural parts, and demonstrate the quality repeatability for producing full-scale structural parts. What we are looking for is funding to cover costs, to cover training of technology transition partner, and to be able to prove the improvement in process quality, part quality. Please note that the work that we have done has been such that it does not require scientists to perform process control. It is amenable for direct use in an industrial operational environment. And finally, here is our contact information. We are Applied Optimization. My name is Anil Chowdhury. My phone number is given below. Please do, visit us on the WebEx for the demonstration of our process control software. We do have test samples. I can't hand them to you today since this is virtual, but we are located in Dayton, Ohio, just 4 miles of Wright-Patterson Air Force Base. So if you happen to be in Dayton for any other work at the Air Force, please do stop by at our facility. We can demonstrate the method that we use for process control and work with you on your application to produce high-quality structural part. Thank you very much for your attention, your time, and we look forward to working with you. Have a good day.